Early next year, we intend to introduce topology optimization. You see here a design volume, this block, and within this volume, we're going to let the software create the optimized shape. Now, another thing that we have in this block is the yellow zone, and that's a keep out region. So we want that no material is created over there. And there's 3 axes, and we're also going to use those axes. Now, we're only going to simulate on half of the model because it's symmetrical. It's a symmetric model and a symmetrically loaded model. We're going to define the zone where we want to have material. So in that zone he can have material. We're also going to define a symmetry plane and the material. So based on the material, software can take into account the properties of the material. Further on, we're going to say that around that central hole that you see highlighted over there on the left, that we want at least 1 millimeter of material. For example, that we want a full zone for an axis. And at that location the part is also fixed, so that the part cannot move around that hole. We're also going to define an offset around the right hand hole. And finally, I'm also going to add the shape in the middle, the yellow one. And on that yellow shape, I do not want any material in it. So it's a keep out zone. In the next step, I'm going to define my loads. So on one hole, we're going to apply a load of 100 Newton. So that's this hole. And I'm also going to define the direction of the load from this point toward that point. So in that direction, on the hole, there's a load of 100 Newton. Finally, I'm going to define the setup of my simulation. I didn't apply a maximum displacement or something. I'm just saying, well, try to have an optimum shape when the weight is divided by 4. And we can define the precision of our results. So the more fine we make, the slower the simulation will be, but also the more precise the result will be at the end. I'm going to show that in a minute. So it's a live solve. I didn't pause the movie, and here you see already the optimized shape. Let me hide the solids, and here you see the optimized shape we got. Here near the edges it's a bit rough, but again, if we give it more precise setting during solve time, you're going to see that edges will be better. This can be shown in this model. So here you got the same setup, except here you see you got a much more precise result around the edges of that hole. So this is a faceted model, and maybe you can immediately already use that for printing or machining. Could be that it's already precise enough for your purposes. One of the cool things we also added in 11 is the possibility to combine classical features with these faceted models. So here you see the same model as my first live optimization. For example, let us create some geometry using classical modeling techniques. In this case, an extrude. So I'm defining this shape, and when we say that we can combine it with faceted models, I can subtract, for example, this shape from this part, and as you can see, let me just hide the data plane. We just created in this faceted model and cut out using a classical modeling operator and this shape. Another example of an optimization is, for example, this bracket. It was used for a contest on Topology a few years ago, but here you see, for example, the design shape of a volume where we allow to have material, and you see here inside the optimized shape of, for example, this bracket. So it's a method that gives you, on a very fast way, already some shapes that can inspire you for your final product. And because of the precision of the result, maybe it's already good enough for direct production purposes.